Now let's look at some examples to show you how to develop mathematical formulation to optimize a flowsheet structure. Let's look at example 1.2 that was introduced in topic 1. In this example, there are three candidate reactors. The reaction is use A to produce B, and the minimum productivity of B is 10 kmol per hour, and up to 15 kmol per hour of reactor A are available, and the price of A is about $2 per kilomole. We are also given the conversion in each reactor, and also the operating cost of the reactor. The operating cost includes the fixed cost and also the variable cost. The variable cost depends on the inlet flow rate into each reactor. The question is to develop a mixed integer linear programming formulation, MILP formulation, to select reactors and also to minimize total operating costs. We first need to define the problem. In the problem definition, we must be clear about what is given and what we want to determine. In this example, we are given the superstructure and also some data, such as reaction conversion rate, reactor operating cost, cost coefficient, raw material cost, maximum feed rate of raw material, and minimum productivity of product B. What we want to determine which reactor or reactors are selected. We also want to determine the optimal feed rate of A to the selected reactor. And we also want to determine the optimum production rate of B. The objective is to minimize total operating cost. Similar to other examples we have discussed in previous topics, we also use some symbols to denote those data that are given. And for this example, we can only make assumptions like steady state without any uncertainty or dynamics, and we don't consider recycle stream in the process. Next, we need to define variables. Variables are usually used to denote what we want to determine, as we want to determine which reactor or reactors are selected. So we need to define integer variables y1, y2, y3. y1 is used to denote if reactor 1 is selected or not. If y1 is equal to 1, that means reactor 1 is selected. If y1 is equal to 0, that means reactor 1 is not selected. Similarly, y2 is used to denote if reactor 2 is selected, and y3 is used to denote if reactor 3 is selected. The values of y1, y2, y3 can only be 0 or 1. So these three integer variables are also called binary variables. We also want to determine the feed flow rate of A into each reactor. So we define FINR1A, FINR2A, and FINR3A to denote these feed flow rates. And also we want to determine the productivity of B, so we define FB to denote the production rate of B. In addition, we also define FA to denote the total flow rate of A, and also define Fout R1B, Fout R2B, Fout R3B to denote the outlet flow rate of B from each reactor. If you don't define FA, FOUT R1B, FOUT R2B, and FOUT R3B, it is also fine. Okay, now we develop the mathematical formulation for this example as we define variables to denote the total flow rate of A and also the flow rate of A into each reactor. So then we can write FA is equal to FINR1A plus FINR2A plus FINR3A based on the material balance of A. In each reactor, because we define variables to denote the inlet flow rate of A and define the outlet flow rate of B, and also we know the conversion rate of each reactor from A to B, then we can write these three equations to relate the outlet flow rate of B from each reactor with the inlet flow rate of A into each reactor. For instance, FOUT-R1B is equal to FINR1A times the conversion rate of A to B. And then based on the material balance of product B, we can also write the equation to denote the total flow rate of B should be equal to the summation of flow rate of B from each reactor. As we define binary variables to denote if a reactor is selected or not. For instance, we define integer variable y1 to denote if reactor 1 is selected. If reactor 1 is selected, then the feed flow rate of A into this reactor should not exceed the maximum allowable feed rate of A. If reactor 1 is not selected, then the feed rate to reactor 1 should be 0. Then we can write the feed flow rate of A into reactor 1 is less than or equal to the maximum flow rate of A times the integer variable y1. Then it can make sure if reactor 1 is not selected, then the inlet flow rate is equal to 0. And if this reactor is selected, then the inlet flow rate of A should not exceed the maximum flow rate of A. We can develop similar inequality constraints for reactor 2 and reactor 3. In each reactor, we use reaction conversion rate to relate the outlet flow rate of B with the inlet flow rate of A in each reactor. So then we also need to check if the reactor is not selected, then this equation is also satisfied or not. Let's go back to check. For instance, if reactor 1 is not selected, the inlet flow rate of A into this reactor FINR1A is equal to 0. Then we can make sure Fout R1B is also equal to 0. That means if reactor 1 is not selected, this equation is satisfied. And if reactor 1 is selected, then we also have this equation to ensure the outlet flow rate of B is equal to the inlet flow rate of A times the conversion of A to B. As we have discussed before, we can also use two slack variables in this equation. Then we can write F O U T R1 B is equal to F I N R 1A times conversion R1A plus S R1 minus S R let's see, SR1A minus SR1B. Then we also need to make sure if the reactor is not selected, then these two select variables should be 0. Then we write SR1A is less than or equal to M R1, the big M value for R1 times 1 minus Y1. Also SR1B less than or equal to M R1 times 1 minus Y1. We can also combine them as 1, right? We can also combine them as SR1A plus SR1B is less than or equal to MR1 times 1 minus Y1. Similarly, you can introduce slack variables for the equation for R2 and for the equation for R3. Both of them are correct. Next, we also have some limits in this example. We have the maximum feed rate of raw material A. Then we can write FA, the total flow rate of A, should less than or equal to the maximum rate of A. And also we need to satisfy the minimum productivity of B. Then we can write FB is greater than or equal to minimum productivity of B. All variables should be non-negative. If we have introduced slack variables, then we also need to add slack variable here. SR1A, SR1B, SR2A, SR2B, SR3A, and SR3B should also be non-negative. Finally, we can write the object function. The objective is to minimize total operating cost. The total operating cost includes the raw material cost of A and the operating cost of reactors. Then we can write this function. In this function, we can see the first term is raw material cost of A. It is calculated by the price of A times the flow rate of A. For the operating cost of each reactor, operating cost is calculated by a fixed cost plus the variable cost. As we define integer variables to denote if a reactor is selected or not, then we should use the fixed cost times the integer variables and plus the variable cost. The variable cost depends on the inlet flow rate. As we already ensure, if the integer variable is 0, then the inlet flow rate to the reactor is also 0. That means we can make sure if the reactor is not selected, then the operating cost is equal to 0. And then this is same for reactor 2 and reactor 3. Okay, now we can also calculate the degrees of freedom. EOF is equal to, even in this example, we define integer variables, but we can use the same definition to calculate the degrees of freedom. The degrees of freedom is equal to the number of variables Let's first to see if we don't introduce slack variables, how many variables we have. We have 11 variables minus how many independent equations. We have 5 independent equations, right? The degrees freedom is equal to 6. If we use the slack variables, we can also calculate the degrees of freedom. DOF is equal to the number of variables as we introduced 6 additional slack variables, so we have 17 variables. And how many independent equations we have? We still have 5 independent equations, so the degrees of freedom is equal to 12. This is because we introduced additional 6 slack variables, but we didn't introduce additional equations to relate these 6 slack variables. That's why we increase the degrees of freedom. Let's look at another example, example 8.1. In this example, we are given the superstructure which contains several options to produce product C using raw material A and B. From this superstructure, we can see product C can be produced from plant 1 using raw material B. C can also be produced from plant 1 and plant 2 using raw material A and B. C can also be produced from plant 3 and plant 1 using raw material A and B. Some data are given. For instance, the mass balance in each plant is given, and also for each plant, the operating cost is also given, which includes a fixed cost and a variable cost. The raw material cost is also given, and the revenue, the price of the product C is also given. There are also some limits, like the outlet flow rate of B2 from plant 2 should not exceed 5, and also the market demand for product C should be less than or equal to 1 ton per hour. The question is to develop a mixed integer nonlinear programming model to maximize profit. Okay, first we define the problem. We write what is given and what we want to determine. In this example, we are given the superstructure and some data that we discussed just now. We want to determine which plant is selected. We also want to determine the optimal flow rate for each selected plant, and also determine the optimal production rate of the selected plant, and also the production rate of product C. We use several symbols to denote the data that are given to us. For instance, we use the symbol CF1 to denote fixed cost coefficient of plant 1, and also we use symbol TC to denote revenue, a price of product C. Before we develop a mathematical formulation, we need to make some suitable assumptions. In this example, we can only assume steady state without any uncertainty and dynamics. No recycle stream is considered. Then we define variables to denote what we want to determine. We define the flow rate of raw material A, flow rate of A into process 2 and 3, and also flow rate of B and the flow rate of B from process 2 and 3, and inlet flow rate into process 1. And then we define the flow rate of product C. as we want to determine which process or plant is selected. Then we define integer variables y1, y2, y3 to denote if a process is selected or not. Then we can develop a mathematical formulation for this example. We first write the object function. The objective is to maximize total profit. It can be calculated by the revenue from sale of product C minus raw material cost and minus operating cost of each process or plant. Then we can write this function. It's not too difficult. The first term is the revenue from sale of product C using the price of C times the flow rate of C, and these two terms are raw material A and B cost. This is the operating cost from process 1. This is a cost from process 2. And this is a cost from process 3. As the cost of each process includes a fixed cost, so we need to use that fixed cost times integer variables to make sure if the process is not selected, then the cost will be 0. As we define the total flow rate of A and the flow rate of A into process 2 and 3, then we can write the total flow rate A is equal to the flow rate into the process 2 plus flow rate of A into process 3. We can also write the material balance for raw material B. For each process, the mass balance is provided. That means if that process is selected, then we should have those mass balance equations. If the process is not selected, then those mass balance equations should be deactivated. We can introduce two slack variables into those mass balance equations, and then we need to make sure if the process is not selected, then these two slack variables should be 0. We also want to make sure if the process is not selected, then the inlet flow rate and outlet flow rate should be 0. Based on this, then we can finish these constraints for process 1, process 2, and process 3. We also need to satisfy some limits. The productivity of C should be less than or equal to 1 ton per hour, and also the outlet flow rate of B from process 2 should be less than or equal to 5 tons per hour. All variables should be non-negative. The integer variables y1, y2, and y3 can take value only 0 or 1. Then we finish the mathematical formulation for this example. I don't think it's too difficult, right? Let's calculate the degrees of freedom for this example. DOF is equal to the number of variables. We have 17 variables minus the number of independent equations, that is 5, and then the degrees of freedom is equal to 12. That means we have 12 independent variables. These variables can be y1, y2, y3, 3 integer variables, and 6 slack variables s11, s12, s21, s22, s31, s32, and inlet flow rate of A into process 2 and process 3, and the supply of raw material B, that is B1. If we know the value of these variables, then the values of other variables can be determined from those 5 independent equations.